Thermochemistry 2, Part 1, Spontaneity and Entropy. What we're going to be looking at today is Enduring Understanding's 5-point-E, which states, chemical or physical processes are driven by a decrease in enthalpy or an increase in entropy or both. And Enduring Understanding 5.E.1, entropy is a measure of the dispersal of matter and energy. Specifically, we're going to be looking at the First Law of Thermodynamics, spontaneous processes, entropy, positional entropy, and then finally practice identifying low and high entropy states. Spontaneity, entropy, and free energy. The first law of thermodynamics states energy can neither be created nor destroyed, and the energy of the universe is constant. Spontaneous processes are processes that occur without outside intervention. Spontaneous processes may be fast or slow depending on the situation. Many forms of combustion are fast, while the conversion of a diamond to graphite is quite slow. Let's look at the definition of entropy, which we represent by the letter S. Entropy is a measure of randomness or disorder. The driving force for a spontaneous process is an increase in the entropy of the universe. Entropy is a thermodynamic function describing the number of arrangements that are available to a system. Nature proceeds towards the states that have the highest possibilities of existing. So in this graphic over here, we're looking at the dissolution of sodium chloride increases entropy. So the less random or the less entropy state is when sodium chloride appears as a solid and the water molecules surround the sodium chloride. Entropy will increase as the water molecules pull the sodium ions and the chloride ions off of the solid and things become much more random. Let's look at positional entropy. The probability of occurrence of a particular state depends on the number of ways or microstates in which that arrangement can be achieved. So a solid has only really one microstate, therefore a low entropy. A liquid will have a number of different microstates, so an increase in entropy. And then finally, a gas will have the highest entropy with a number of different microstates. Entropy increases with the number of microstates of the system. An increase in the number of microstates leads to a positive value of S. So let me say that again. A positive value of S translates to an increase in entropy. So as a solid, we have low entropy. As a liquid, we will have higher entropy. And in the gas state, we will have the highest entropy. Therefore, an increase in any of the following will lead to an increase in entropy. If we see an increase in temperature, volume, or the number of independently moving particles. Let's look at an example. For each of the following pairs, choose the substance with the higher positional entropy per mole at a given temperature. So in our first example, we are looking at solid carbon dioxide and gaseous carbon dioxide. We're trying to determine which one is going to have the higher positional entropy, or in other words, be more random. If you said the gaseous carbon dioxide, you are correct because the gaseous carbon dioxide is going to have more microstates and be much more random. Let's look at the next one. Nitrogen gas at 1 atmosphere versus nitrogen gas at 1.0 times 10 to the negative 2 atmospheres. What we are comparing here is pressure. So which one will have the higher entropy? If you chose the one with the lower pressure, you are correct. The less pressure it has, the more volume it will have, and therefore a higher entropy. So this is the correct answer for the second one. Let's do some more practice. For each of the following pairs, choose the substance with a higher entropy per mole at a given temperature. So what I'd like you to do is stop, pause the video, choose the substance that you believe will have the higher entropy, and then check your work. Welcome back. Let's see how you did. For the first one, we have argon as a liquid or argon as a gas. If you chose argon as a gas, you are correct because that will have a greater entropy. Helium at 3 atmospheres of pressure or helium at 1.5 atmospheres. If you chose helium at 1.5 atmospheres, you are correct. The more pressure that we have on our substance, the less entropy it will have. So helium at 1.5 atmospheres is the one with the higher entropy. 1 mole of neon in 15 liters or 1 mole of neon gas in 1.5 liters. If you chose the 1 mole of neon in 15 liters, you are correct, because obviously the greater volume you have, the greater the ability of the particles to move and form different microstates, so this would be the correct one for the greatest entropy. Water as a liquid or water as a solid? The correct answer for this one would be water as a liquid, because a liquid is going to have greater microstates than water in the form of ice. Predict the sign of entropy change for each of the following processes. Now remember, if you use a plus sign, that means that entropy is increasing. If we have a negative sign associated with an entropy change, that means the entropy is decreasing, or it's becoming more organized, less random. Solid sugar is added to water to form a solution. Well, we know, based on this situation, that we would be increasing our entropy. Therefore, the sign that we would use to show this change would be positive. Iodine vapor condenses on a cold surface to form iodine crystals. So we're going from a gaseous situation to a solid situation. Therefore, the sign that we would associate with this change in entropy would be negative.